So let's begin. You ready, right? You're muted.
Okay. Yeah.
Yeah. So I'll begin with the introduction. So hello everybody. On behalf of ISI Bangalore students and research scholars, I welcome you all to the last session of the last day of the limit camp. Today we have with us our speaker Ruchira Mukherjee. She is interested in number theory and she will be presenting on the topic the cycle lemma and ballot problem. Please note that this talk shall be recorded and uploaded to our YouTube channel, so please check it out if you need anything. I would like to hand it over to the speaker now.
Right. So while I'm in the talk, I will not be able to see the chat box. Everyone is free to interrupt me if they don't understand anything. And this is going to be an interactive talk, so I would want everyone to respond to the questions I'll be asking, or at least think about it. Right. So let's present my screen. Right. Can people hear me now and see my screen?
Yeah, you're audible and the screen is visible.
Okay. So let's first introduce the problem. Suppose that in an election, candidate A receives A votes and candidate B receives B votes, where A is greater than or equal to KB for some positive integer k. We compute the number of ways the ballots can be ordered so that candidate A maintains more than k times as many votes as candidate B throughout the counting of the ballots. For example, like if it's happening in the real time, let's say we start with candidates A and B. These are rods for A and B. And votes will be in the form of an abacus. These things will be votes. And now candidate A comes and puts the first voter comes in and puts the bead in the A's section. So suppose k is equal to 3, then I must have at least 4 beads for A before there is a bead for B. Because at every step, we need the number of voters for A to be greater than 3 times the number of votes for B. And now if another voter comes, they cannot vote for candidate A, but have to vote for, they cannot vote for candidate B. They have to vote for candidate A instead. We want to compute the number of ways this thing can be done. Okay. So I would give people at least 3 minutes time to think about the problem. Think about the ways this problem can be solved. Like you can think about whatever ways you can. You don't have to completely solve the problem. Just think about the problem. Or ask me any questions if you don't understand the problem.
Ruchira, there has been a message in the chat.
Right.
Shurjendu Kaur has asked, can we
Yeah.
somehow induct?
Can we?
Somehow induct.
Okay. Yeah, sure. You can try the induction now. I will be presenting three different solutions to this problem. And one of them will be using the cycle lemma. All right, so kind of 3 minutes are over. I would like to ask the audience, like, just speak up, unmute your mic and speak up. Like, what are the ways you have thought this problem can be approached? No one is judging you, so.
A is like greater than 3b in this
Okay.
case. So
Mm-hmm.
we could take values like A is equal to 3b plus 1, A is equal to 3b plus 2, and so on and so forth.
Yeah.
And then for each case, we could probably like, suppose we take A equal to 3b plus 1, and then we uh, count the number of ways we can, like
Right.
the number of combinations in this case, and then sort of find out a pattern and then probably use induction to assign that for the other values 3b plus.
Right. Any other ideas? Okay, so induction is actually a right way to do this. We will approach this problem after looking at a different method to solve this problem. I find this method quite interesting, and that is the reflection method. Anyways, the answer to this problem is a minus kb by a plus b times a plus b choose a. This is like a factorial. A plus b choose a is a plus b factorial by a factorial and times b factorial. And this you can verify to be belonging to integers. So now this kind of looks like the total number of distinct permutations, and this is a probability that's multiplied to this number, so that the number of ways becomes this times a plus b choose a. The first method we will be solving this problem with is the reflection method, followed by induction, you can see it here, and the cycle lemma. We can think of a Ballot permutation as a lattice path. Lattice path means this kind of thing. So if we choose, like if there's a vote for candidate A, we express it as up steps 1, 1. So suppose we start at the origin and candidate A receives 1 vote. Then we go up 1 step to the right and to the upward direction, that is here. This is time and the number of votes. And if there's a vote for B, then we take this down step 1 comma minus k. If k is, suppose, again, good illustration would be 3 because it keeps in between these -5 and 5. So then if there's a vote for B, then we go down here. The number, like the problem tells us to find the number of ways this graph can be drawn with this or these allowed steps, such that the graph always stays above the x-axis. Like the number of votes would be greater than the votes for A would be greater than the votes for B till the end where um, they can meet, because A is taken to be greater than or equal to KB, total number of votes for candidate A. Right. We define a down step to be one that starts above the x-axis and ends on or below the x-axis, to be a bad step. So suppose we have a graph that goes, like we can consider this graph itself. This would be a down step, this thing here. And then it can go up and up and up, say. There are votes for A now. And then if it goes down again, this would again be a down step. But this, yeah, these are down steps. These are actually bad steps. Yeah, so these are bad steps. It goes below the x-axis. This is a bad step. This touches the x-axis. But this is not a bad step. This is just a down step because it stays above the x-axis. Okay. Now, to count the number of ways where the graph stays above the x-axis till the number of voters A plus B is finished. Say the total number of votes is 15, then we count till here, and this can stay above or below, as is the values of A and B. We divide the number of cases as BI. Let BI denote the set of bad paths. Bad paths are where the graph goes down or touches at least once. So this would be a good path, something like this. It does not touch, but anything other than that would be a bad path. Always starting at the origin. Right. Let BI denote the bad set of bad paths whose first bad step ends I units below the x-axis. Note the thing first bad step, where I is between 0 and k. So up till then, all the steps that had been taken were at least votes for A or the votes for B, such that the graph stayed above the x-axis. It is the first bad step that ends I units below the x-axis. Now, BK are disjoint. You can see that clearly, right? The first bad step cannot end at both I and j units below x-axis for I not equal to j. The paths in BK are exactly those paths that start with a down step. Why? because for because for a path to be k, the first path to be k units below the graph would mean that there have been no votes for A, or that the starting point would have to be origin, right? So BK would be those paths that start with a downstep. So the cardinality of BK, the number of ways this can be done, is A plus B minus 1 choose A. Because we are disregarding the first bad step, like if this is the starting vote for B, then we have A minus 1 time left, like A minus 1 voters left. A plus B minus 1. Sorry. And now out of these, there are A votes for candidate A. So the number of such ways would be A plus B minus 1, choose A. And this is already a bad path because it directly went below the x-axis in the step 1. Now we will show that for each of these BI, the number of ways would be the same as the number of ways for BK. How is that true? There's a special technique to prove this called the reflection method. So suppose, let's just take the k is equal to 3 case itself. Suppose we have a graph that goes like this. 4 votes for A, 1 vote for B, 1 vote for A again, 1 vote for B. This is the bad step. It goes below the x-axis. And this is a member of BI, B1, because it goes 1 unit below the x-axis. B0 would be just touching the x-axis. So then I say there's a vote for A, and so on, whatever follows after this, like follows right after this, can be anything. But we are concerned more about what happens when it first touches or goes down the x-axis. From this point, we start to do a sort of rotation, I would say, but as it's happening below the x-axis, we kind of say it's a reflection. So we take this path here and rotate it and draw in this region. So how would that look? It would look like there are 4 votes for A. So go down 4 votes. 4 votes for A. Then there's a vote for B. Go up. There's a vote for A. Go down again. And there's a vote for B. So now, every such graph in B1, in this case, say it's for BI also, we can consider this to be a valid graph as well. The other points can remain like the initial graph. So the blue graph and the black graph are in bijection by this setup that we are doing, right? This proves that for any I, the cardinality of BI would be the same as the cardinality of BK, because this the blue graph belongs to BK. The first step itself takes k steps down, like a vote for B. So now, what are the total number of good paths? If the cardinality of BI is the same as BK, which is A plus B minus 1, okay, the number of total paths is actually A plus B choose A. And now we subtract the number of bad paths, which would be I taking values from 0 to k, both included. So this would be k plus 1 values for I. And we subtract a plus b minus 1. Simple calculation would give us this answer. So we are done.
Just 1 second.
Yeah.
Gurjendra Kaur also provided a solution in the chat. I would like you to just check the chat once
Yeah,
for
yeah.
that. Just check the
Oh,
chat. Yeah, it is a
oh.
bit long to say verbally.
Uh,
In
okay.
call versus, yes.
Let F A B denote the number of ways of arranging. Yeah, 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 yeah. Sure. Yes, this is the exact thing that we are going to explain in the second method. Brilliant students here. Okay. So the second method is induction. Let NKAB be the number of ways in which A plus B ballots, where A is greater than or equal to KB, can be ordered so that candidate A maintains more than K times as many votes as candidate B throughout the counting of the ballots. Now for A greater than 0, we have NKA0 is equal to 1 because there's just one vote for A, and there are just votes for A and 0 for B. So throughout whatever value K is in the positive integers, uh, there's only one arrangement because all the objects are of same type. For B greater than 0, we have NK KB, comma B is equal to 0. Because whatever way we count, the process will have to have the number of votes for A greater than equal to the number of votes for B, disregarding the last step. Even including the last step, that would be true. But we want to count the number of ways where, while the process is going on, the number of votes is strictly greater than k times the number of votes for A. Okay. So the base cases for induction are these, and they both satisfy this formula. You can just plug in A is equal to KB here, and A is equal to whatever A, and B is equal to 0, and just check this. Here is a solves table for A and B taking these values, and K is 3 here again. 3 is my favorite number, so yeah. And all of these would be 0, so I've kept them blank. They're all 0. You can check that if A has 7 votes and B has 2 votes, say, then you can have something like A four votes for A. Then say there's a B. We exhausted 7 votes for A, and there's another vote for B. Now the other ways would be just shifting B to these places. So there are 4 ways to do this. That's why this entry is 4. And so on and so forth. Now, what do you observe from this table here? Ignore the 0 values. What are, like, induction, right? So you go from an initial, like the previous steps to the next step. So can you tell me how 9 can be obtained? 9 is obtained by 4 plus 5. So you add up these entries and obtain 9. You add up these entries and obtain 15. And so on and so forth. So if you want to extend the table, it would just be like 0, 0, 0, 0 here in this case as well. And here it would be something like 6, 7, 8, 9, 10, and so 15 plus 7, and 0 plus 22, it would be 22. so on and so on. Right. Exactly the same thing. So the number of ways of A plus B votes can be arranged, blah, 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 would be this, because NKAB is NKA, comma B minus 1 plus NKA minus 1, comma B. So by induction hypothesis, we can assume that these follow the same formula as this one here. And the sum of these would give me this. And we can close the induction. So we come to the last proof of this problem using the cycle lemma. So what is the cycle lemma? Suppose you're given 6 squares and 3 circles, and you can arrange them in various different ways, but something is common between these 3 ways. The number of squares is always greater than the number of circles afterwards. Can you see it?
Yeah, it's visible.
Yeah. Right. So you can observe this as well. Yeah, this is quite redundant after all the math we have been done. Yeah. So the definition, a sequence of a finite number of boxes and circles is K dominating for K in the natural numbers. If for every position I between 1 and L, both included, the number of boxes in the sequence is more than K times the number of circles. To correspond this to the ballot problem, we can consider the votes for A to be represented by boxes and votes for B to be represented by, not boxes, circles. So given a feasible sequence, like here K is say 1, and this is of course a feasible sequence, because the number of votes for A is strictly greater than the number of votes for B. The number of squares is strictly greater than the number of circles. There are 9 cyclic permutations in total. All of these are listed. Just draw this around a circle and start counting from a specific direction. You get these. Can you tell me what are the number of 1 dominating sequences here? This is 1 dominating. We started at the feasible one. This is also 1 dominating, I think. This is not 1 dominating. Is it 1? Oh, okay. Greater than 1, right? What was the definition? The number of boxes more than K times. Okay, more than. Okay, so this would be 1 dominating. I can find 3. Can you find more than 3? No, right? Because this would have equal numbers, so this is not something we want. And we have 2 circles here and then once.
Just 1 second.
Okay.
Some people were asking for asking you to repeat the definition of 1 dominating sequences. They did not quite understand.
Oh, okay. So a sequence of a finite number of boxes and circles is called K dominating if for every position in between 1 and L. So for a sequence like this, for every position, that is, you consider these positions here, the number of boxes in the sequence is more than K times the number of circles. So here, if there's only one box. So of course it's, so when we take k is equal to 1, we say it's 1 dominating. So the number of boxes are definitely more than the number of circles. Same here, here, and so on. Here also it's fine. The number of squares is 4 and the number of circles is 1. It's of course 4 is always greater than 1. 4 is always greater than 2. 5 is greater than 2. 6 is greater than 2. 6 is greater than 3. Okay? So now the one dominating sequences can only be these three, right? Is the thing clear for the one who was asking the definition? You can
Yeah,
speak.
both of them said yes.
Okay, okay. Try speaking up, okay? All right. So for n, suppose we have a fixed sequence. The sequence is given to us of m boxes and n circles. And now the number of cyclic permutations would be m plus n, simply because we are taking the fixed sequence and we are just rotating it if we arrange the boxes and circles like this. Okay. Such that m is greater than or equal to kn, then there are exactly m minus kn out of the m plus n cyclic permutations that are k dominating. This is the theorem, like the cycle lemma. And we will prove this. In order to prove this, first consider the example. Like, I will illustrate how the proof goes through an example. So we are again given this sequence. We arrange them in a clockwise direction. Now, if we want to compute the number of one dominating sequences in this particular order, then notice that for every circle, there has to be at least one square before it, right? So if we take out these two elements from this sequence, the number of such ways of counting would not affect the number of ways of counting for the initial sequence, right? So if we take out the 9th and 8th, right? So if we take out these two elements, to count the number of k-dominating cyclic things for this sequence alone would be the same number as counting the k-dominating permutations for the initial sequence. So we continue this process. And we are left with 3 boxes. These 3 are the exact cyclic permutations that are one dominating. What do these correspond to? This corresponds to starting with 1. We are given the initial one. So these are 4 boxes, 2 circles, 2 boxes, 1 circle. Starting from position 2, it would be 3 boxes, 2 circles, 2 boxes, a circle, and a box. Starting from the 7th position, we will have 2 boxes, a circle, 4 boxes, and 2 circles. These are precisely the same things here. You can match this. You can take a screenshot and match this if you can't see it right now. They are not in the same place. Right. So the proof goes exactly as the procedure illustrated in the example. Arrange these m plus 1 figures around a circle in a clockwise direction or anti-clockwise direction, but you need to be counting it like if it's in a clockwise direction, you need to start from a circle and then go back to cancel out a circle and a square. And if you're arranging it in an anti-clockwise direction, you need to go front. So you cannot arrange it in clockwise and then start canceling in the same direction. Okay, so just a particular direction. And following along the direction of arrangement, notes that removing a subsequence of k squares followed by one circle does not affect the count of the number of k dominating permutations. Here k was 1, so we were cancelling out a circle and then a square before that. For k dominating, it would be cancelling out a circle and k squares. We end up with m minus k in boxes, and these are precisely the permutations that begin with the box and yield a k dominating permutation. So basically now the probability of, if all arrangements are feasible, then the probability of having a k dominating permutation would be this. And the number of ways of arranging it would be and this is exactly what we want. Right. So just saying, these are the references I've used for giving this, presenting this, and you can check these out as well. The first people to come up with the cycle lemma as a procedure for solving the ballot problem were these people here, Motzkin and Voretsky. Yes. Right. So any doubts or any questions?
No. Thank you very much for the talk, Ruchadi.
Yeah.
If anybody has any questions, please feel free to ask.
Yeah.
All right. In that case, Shanchanda, please.
Hi, hi.
Yeah.
Yeah, so yeah, thank you, Ruchira, for your and so this is the last session for limit camp for category A, and I hope that you enjoyed the whole limit camp, and I hope this competition will go on further and there'll be more camps next year. And we will share a small feedback form. You can put up your feedback over there, and yeah, that's more or less. Thanks. Yeah, right. Yeah, poster session.
Yeah,
But
we have the post
officially, as
session.
in the speakers, this was the last talk.